Greetings. Our senior project this year was to create a device that would measure the fluorescence decay of rubipi. My name is Richard Critchlow.
I'm Jacob Cartwright.
I'm Andrew Cruzy.
I'm Ethan Lewis.
And my name is Juan Lum.
In fluorescent spectrometry, excitation decay time of a material provides insight into a material's physical chemical properties. This project will allow for the accurate measurement of fluorescence decay time of an aqueous solution of tri-bipyridine ruthenium-2 chloride with an equation as shown, colloquially referred to as rubipi. This project will create an instrument which will allow students at the Grand Valley State University Chemistry Department to study and analyze fluorescence decay time data to determine these chemical characteristics.
The design concept will use a specific light wavelength to excite the rubipi's electrons. Once rubipi is excited, the excitation source will be turned off. The decay time of the rubipi fluorescence can then be measured by the time it takes for the rubipi to stop fluorescence, which occurs in the stable ground state. Rubipi has a very quick fall time, on the order of a few hundred nanoseconds. This means that the excitation source needs to be able to shut off rapidly in order to receive an accurate measurement. The avalanche photodiode, the sensor that captures the fluorescence photons, emits a very low current. This current will need to be converted into a voltage and then amplified in order to be read by an oscilloscope. There's a high potential to collect noise and distort the signal significantly. Rubipi emits large amounts of photons when the excitation light wave is 450 nanometers. The emitted photons from the rubipi sample are around 625 nanometers. Using these physical chemistry characteristics, an excitation source was selected such that it would let us have an excitation wavelength of 450 nanometers. A theater gel filter was selected which will only allow photons with wavelengths around 625 nanometers to pass through. This will allow any excitation light to be filtered out before entering the sensor input, ensuring that only fluorescence electrons are captured by the sensor.
So the plan for this is to have it split up into three separate sections. The main section is going to be the power, which will power the entire project. Then we'll have an excitation source, right? So that's going to be the light or the LED that would shine into the rubipi to fluoresce it. And then finally the collection circuit, which will then take the fluorescence data via a sensor, and we will then take that and analyze it and output it into the oscilloscope. This will all be placed into a light-proof enclosure. This will reduce ambient light noise from various other products. This is our complete layout for the circuit board. Up here we have the excitation source. Here is our power, and then this right here is the collection source. And you'll notice those giant squares, those are for EMI shields that further eliminate outside noise from interfering with our signals, due to the fact that these are such low signals and so susceptible to noise. This is the same design. This is the actual layout, physical layout of the board. Additionally, again, this board will be placed into a small box. Considerations were made to ensure that noise was a minimal risk. There are three different inputs as seen on the bottom. We have a trigger out, a signal out, and a function generator in. Once inside the box, those three BNC cables will be the only input and output that will be into the unit itself. The way this will be used by the chemistry students, so the chemistry department will provide the sample of the rubipi, a power supply, a function generator, and an oscilloscope. The function generator will act as a source for the excitation source, or the LED, and that will be hooked up. The black box will then be plugged into a standard 24 volt outlet, and then it will be outputted a trigger signal along with the signal out, and the trigger signal will be used to find out when the LED turns off and when the actual measurement begins.
From the wall to 24 volt DC power supplies. So the reason for choosing 24 volt DC is because 6 volt circuits as well as the high volt circuit accept 24 volt DC. On the left is the layout. So from the wall to the switch, which have a built-in safety feature and a switch, so you can turn off and turn on the whole thing when you want to. And that will be connected to a 24-volt DC transformer. The 24-volt output will then go to the power processor, and then the output voltages from the power processor will go to the main circuit. So here is a power processor. We have a high V, which will be used to power the APD. 6 volt will be turned into 5 volt, and that will be used to power the excitation and the collections. So the downside of these circuits are the switchings. So that will introduce a lot of noise that we don't want. So that's the reason why we have a separate PCB just for these sections. So 24 volt coming in, going to the capacitors. Then on top, go to that LT8365, going to that whole circuits. Then output a very high voltage ranging from 100V to 200V DC. And on the bottom, 24 volt is trained from using the LT8608 to 6 volt. On the receiving end, on the main board, we have the LDO, which is a noise reduction device. Since the signal is highly sensitive, LDOs are used at the high V and the 6V inputs to reduce noises from the power PCB, which is the previous stage. So the BNCs and the BNC shielded cables are also used to reduce the noises from the power PCB. So the signal, like on the top, we have signal coming in, going to that BNC, going to a pi filter, going to the LR8N8, going to the resistor circuit with the potentiometer to vary the voltage. That voltage will then be going to the APD. Since APD has different breakdown voltage, we have the potentiometer to vary the voltage. On the bottom, we have 6 volt coming in, going to the capacitor, going to 2 pi filter, going to the LT3029. Then one of them will go to the collections, and the other 5 volt will go to the excitations.
Next up, we have the excitation. The excitation needs to be able to be shut off within 100 nanoseconds. So the light from the excitation doesn't pollute our measurement. The other thing to keep in mind was that it has to be within proper safety limits, which eliminated high power light sources such as lasers. Here's how we designed our excitation to get an LED to fall within 100 nanoseconds. First, we have a voltage regulation so that chemistry students can put in whatever voltage they want without blowing up the circuit. Next, we have a high-speed comparator to sharpen the fall time off of the function generators outputted square waves. And then we have a Darlington pair array to pull the LED down. And then finally, we have the trigger output. Here's the board layout for our excitation circuit. One thing to note is that we included a 3v3 voltage regulator because the comparators need their own 3v3 source. Here's our measurements of the excitation source. As we can see, we fall within the 100 nanosecond fall time. And on the left, you can see the measurement of the fall time of the LED versus the fall time of RuBiPi. Here we can see the decay time of the exponential of the LED, which is 22 nanoseconds, which is well below our rated spec of 100 nanoseconds.
Next up is the collection portion of the project, and there was 2 main specifications. The first was that the peak voltage of the output signal must be at least 100 millivolts, And the second was that the bandwidth of the entire system must be at least 10 megahertz. The collection side of the circuit consists of 3 sections: photodiode and transimpedance amplifier, the inverting gain stage, and 2 Sallen-Key low-pass filters. Here is the LT Spice layout of the collection circuit. The individual sections talked about in the previous slide are kind of boxed. As you can see, this slide is a shows the output waveform when that blue 1 microamp input current was put into the system, and it shows that we're getting over 200 millivolts, so that's within our spec. Here is the transimpedance amplifier schematic from our Altium design. And there's the linear regulator on the far left, which allows us to change that the breakdown voltage that we send to that photodiode. Next up is the inverting gain stage, which essentially just takes that negative signal coming out of the transimpedance amp and flips it, but also increases the gain by 3.3. Next are 2 second-order Sallen-Key low-pass filters, even though only one is shown in the image. And here's the entire collection circuit layout. And some notable features of this part of the circuit are that there are 0 ohm resistors before and after each op amp, so that sections could be bypassed if need be. And there's also EMI shields covering each of the op amps in this section for noise prevention.
Gain of the avalanche photodiode is dependent on the avalanche photodiode's breakdown and reverse bias voltage ratio. This curve can be seen in the graph on the right. The avalanche photodiode breakdown voltage is 160 volts to 200 volts, which depends on the properties of the integrated circuit during the time of manufacture. Using a controlled test setup, each avalanche photodiode was tested to determine if a desired output waveform could be achieved. The desired output AC waveform, as shown above in yellow, for our given test of a 0.3 molar aqueous solution, should have a 600 millivolt peak-to-peak output wave. Testing various avalanche photodiodes show the design was successful in achieving the voltage peak-to-peak and fall time while still achieving the system's SNR specifications across our variable voltage range.
And finally, we have our SNR specifications. Noise was a big issue for us since the very early stages of this project. And as such, we put a lot of thought into how we can reduce it and mitigate it. And our specification was that we must have at most 25 dB of SNR. And we calculated the SNR for our output in 3 separate ways using different references, and all of which got us around 30 to 34 dB, which is well above our rated specification.
So in conclusion, our project was able to meet specifications. We have a fall time of our LED, which about 200 or 22 nanoseconds, which is well under 100 nanoseconds. We have 30 dB SNR, 30 dB plus, right? And on the left here, you can even see our measured signal versus the theoretical signal, which shows that we are clearly getting a good result that matches what we would expect to be matching. And including even on the right with the fitted exponential, our results match what we should be expecting. And our project fits the specs given to us for their requirements. Thank you.